Welcome to this explainer on the Øresund crossing. We are diving into a high-stakes engineering thriller today, where architects and builders had to conquer both the sky above and the crushing depths of the sea below. Because, this isn't just about getting from point A to point B. It's about figuring out how to make a massive, multi-lane piece of infrastructure completely vanish into the ocean. So let's just lay out the problem. How exactly do you connect the bustling capital of Copenhagen in Denmark over to Malmö in Sweden when the very environment flat out refuses to cooperate? You see, if you build a bridge high enough for colossal container ships to pass safely underneath, well, it's going to crash right into the flight paths of passenger airplanes. But if you build a bridge low enough to keep those planes safe, you completely block vital global trade routes. It's essentially an impossible logistical knot. Part 1. The ultimate engineering dilemma. Before a single drop of concrete could even be poured, engineers were staring down a massive roadblock. On one side, you have a terrifying aviation conflict. The Copenhagen airport, Kastrup, sits right at the edge of the street. If you build a soaring suspension bridge there, its massive towers are going to violently pierce the mandatory approach zones of landing aircraft. You're looking at an absolutely unacceptable, catastrophic collision risk. But on the flip side, we have the maritime conflict. Build a low bridge, and you essentially slap a physical padlock on the Baltic Sea. You'd be cutting off massive cruise ships and container vessels, which would trigger immediate, staggering global economic disruption. So the bottom line here is that engineers were entirely trapped. They couldn't just draw a straight line of steel and concrete across the water without triggering either an international aviation disaster or total economic paralysis in the ocean. The environment was basically demanding that this bridge shouldn't exist. Part 2. The hybrid megastructure solution. To solve the impossible, they had to completely rewrite the rules of what a bridge could actually be. Think about it. If you can't go over and you can't go under, well, you have to do both. They split the crossing into 3 distinct, highly specialized parts: a 7.8-kilometer cable-stayed bridge, a 4-kilometer artificial island named Perberholm, and finally, the 4-kilometer Drogden underwater tunnel. This design flawlessly transitions a heavy 4-lane highway and a dual-track railway across 3 radically different environments. Honestly, the narrative of this megastructure is absolutely cinematic. They decided to build a massive, soaring bridge strictly on the Swedish side, where the airspace actually allowed for it safely. Then, right in the middle of the strait, they would seamlessly drop that massive highway down onto a custom-built island, and then plunge the entire operation deep underwater into an immersed tunnel long before it ever reached the delicate flight paths of the Danish airport. Which brings us to part 3, forging Perberholm Island. To transition the unimaginable, crushing weight of a highway and a railway line from the sky down into the seabed, engineers essentially had to play God and forge their own landmass. The sheer scale of this artificial stepping stone is staggering. To create Perberholm, they had to dredge an incredible 6 million cubic meters of rock and sand straight from the seafloor. They literally scraped the ocean floor during the tunnel's excavation and piled it all up in the middle of the strait to act as an anchor for the descending bridge. But the engineering of this island was intensely precise. They couldn't just dump 6 million cubic meters of sand haphazardly into the ocean and hope for the best. The island had to be perfectly aerodynamic and hydrodynamically shaped. Why? Because if they shaped it wrong, it would act like a dam, catastrophically obstructing the critical, natural flow of water and ice between the North Sea and the Baltic Sea. The environment literally dictated the island's very contours. Part 4. Sinking 55,000-ton leviathans. With the island successfully forged and standing strong against the ocean currents, we enter the most tense, most dangerous phase of the entire project, a high-stakes battle against physics. Because the seabed composition meant they couldn't just use a machine to bore a tunnel through solid rock, engineers had to build the tunnel on land. They chose to prefabricate 20 massive concrete tubes, drag them out to sea, and blindly assemble them in the crushing depths of the ocean. To truly wrap your head around the magnitude of these concrete leviathans, we have to look at the numbers. Each individual segment stretched an astonishing 176 meters long, spanned 42 meters wide, and stood 8.5 meters high. Guys, we are talking about dropping entire city blocks into the ocean. And the physical mass is downright terrifying. Each of those 20 segments weighed a staggering 55,000 tons. Just imagine the sheer, unimaginable tension of dangling a 55,000-ton concrete block over a dredged, dark trench in the ocean floor, knowing that a single miscalculation could crack the whole thing in half. Dropping them was a heart-stopping operation. First, engineers had to seal the ends with temporary bulkheads just to get these massive tubes to float. Then, battling unpredictable ocean currents, they hauled them out and positioned them over the dredged trench with absolute pinpoint GPS accuracy. Finally, in a brilliant but super tense maneuver, they ballasted the segments by slowly pumping water into them, intentionally sinking these 55,000-ton behemoths perfectly into the abyss below. And finally, Part 5, the hydrostatic seal. But getting 55,000 tons of concrete aligned in a dark trench is really only half the battle. Think about this. How do you permanently seal these colossal segments together deep underwater, ensuring not a single drop of the ocean gets into a tunnel filled with cars and trains, without using a single underwater welding torch? The answer is one of the most brilliant solutions in all of civil engineering: hydrostatic sealing. Once the segments were placed end-to-end in the trench, engineers simply pumped the trapped water out from the tiny space between them. By removing that water, they created a massive pressure differential. They deliberately used the deadly, crushing hydrostatic pressure of the surrounding ocean itself to squeeze the rubber seals of the segments together. The ocean's terrifying weight did the work for them, violently locking the segments into a permanent, watertight embrace. The engineers didn't just fight the sea here, they used it. If we can literally weaponize the ocean's deadly hydrostatic pressure and turn it into our greatest tool to lock together a disappearing megastructure, what other impossible engineering feats await us in the deep? The depths are waiting, and the blueprints are only getting bolder.